Dear students, in this video we are going to study about the tangent law and the tangent galvanometer, the theory and construction of the tangent galvanometer, current loop as a magnetic dipole moment of a revolving electron. Study about tangent law and tangent galvanometer. What is a tangent galvanometer? It is a device used to detect very small currents, and it is a moving magnet type galvanometer, as the galvanometer will be of two types. One is moving coil magnet galvanometer, moving magnet type galvanometer. Here this working is based on tangent law. And this is the actual tangent galvanometer, in which there is a magnetic compass and a coil of n turns. The number of turns can be selected by using these screws. This is the leveling screw. Now let us see what is tangent law. When a magnetic needle or magnet is freely suspended in two mutually perpendicular uniform magnetic fields, it will come to rest in the direction of the resultant of the two fields. So this is the tangent law, and this tangent galvanometer is based upon this law. Now let us consider the magnetic field B produced by passing current through the coil of the tangent galvanometer, and BH be the horizontal component of Earth's magnetic field. Under the action of these two magnetic fields, B and BH, the needle comes to rest, making an angle theta with BH, such that B is equal to BH tan theta. Now let us see the construction of this TG, the tangent galvanometer. This TG consists of copper coil of several turns wound on a non-magnetic circular frame. The frame is made up of brass or wood, which is mounted vertically on a horizontal base table, which is called a turntable, with 3 leveling screws. The TG is provided with 2 or more coils of different number of turns. Most of the equipments we use in lab contains coils of 2, 5, and 50 turns, which are of different thickness and are used for measuring currents of different strengths. At the center of turntable, there is a small upright projection on which a compass box is placed. Compass box consists of a small magnetic needle, which is pivoted at its center, such that the centers of both magnetic needle and circular coil exactly coincide. A thin aluminum pointer attached perpendicular to the magnetic needle moves over a graduated circular scale. The circular scale is divided into 4 quadrants, and they are graduated in degrees, each quadrant being numbered from 0 degree to 90 degrees. To avoid parallax error in measurement, a mirror is also placed below the aluminum pointer. Now, before we do the experiment with this staging, we should have some precautions. What are the precautions? We will see now. All the nearby magnets and magnetic materials are kept away from the instrument. Then, using a spirit level, the leveling screws at the base are adjusted so that the small magnetic needle is exactly horizontal, and also the coil, which is mounted on the frame, is exactly vertical. The plane of the coil is kept parallel to the small magnetic needle by rotating the coil about its vertical axis so that the coil remains in magnetic meridian. The compass box alone is rotated such that the aluminum pointer reaches 0 degree and 0 degree. Now we will see the theory of the tangent galvanometer. The tangent galvanometer experiment, when no current is passed through the coil, the small magnetic needle lies along horizontal component of its magnetic field. When the circuit is closed, the electric current will pass through the circular coil and produce magnetic field at the center of the coil. So we will have two fields which are actually mutually perpendicular to each other. They are the magnetic field B due to the electric current in the coil acting normal to the plane of the coil, and the horizontal component of Earth's magnetic field BH. So these are the two magnetic fields which are perpendicular to each other. This BH is its magnetic field, horizontal component of the Earth's magnetic field, and this B is the magnetic field due to the electric current. The resultant position of the pivoted needle will be in this direction, north-south direction, like this. And because of these crossed fields, the pivoted magnetic needle deflects through an angle theta And from tangent law, we have B equal to B tan theta. When an electric current is passed through a circular coil of radius r having n number of turns, the magnitude of magnetic field at the center is given by this equation B equal to mu naught Ni by 2r. And from the equation 3.39 and the equation this 3.40, we will have this equation dH tan theta is equal to mu naught Ni by 2r. The horizontal component of this magnetic field is given by this expression 3.41, that is BH equal to mu naught Ni by 2r tan theta. Then we will study about the current loop, which acts as a magnetic dipole. A magnetic field at a point on the axis of the current carrying circular loop of radius r at a distance z from its center is given by this equation B equal to mu naught I by 2 into r square by r square plus z square power whole power 3 by 2 k unit vector. At larger distances, z is very much greater than r, therefore r square plus z square can be written approximately as z square. So we have B equal to mu naught I r square by 2 z cube into k unit vector, or B equal to mu naught I pi r square by 2 pi z cube k unit vector. If A is the area of the circular loop, that is given by pi r square, and rewriting the equation 3.42 in terms of area of the loop, we will have this equation 3.43, that's B equal to mu naught 2ia by 4 pi z cube k unit vector. So when you compare the equations, this 3.43 with 3.14 dimensionally, we will get Pm is equal to I into A. But this Pm is called the magnetic dipole moment. This is called magnetic dipole moment. And in vector notation, this can be written as Pm vector equal to A vector. This implies that a current carrying circular loop behaves as a magnetic dipole of magnetic moment Pm. So here we can compare these two equations. And the magnetic dipole moment of any current loop is equal to the product of the current and area of the loop. Now we will see about the right hand thumb rule. This right hand thumb rule is used to determine the direction of magnetic moment. And this right hand thumb rule states that if we curl the fingers of right hand in the direction of current in the loop, then the stretched thumb gives the direction of the magnetic moment associated with the loop. So we can find out the polarity of the magnetic field by using these features. If the current is in the anti-clockwise direction, the end will have north pole, and if the current is in the clockwise direction, this end will behave like a south pole of the magnet. Next, we are going to study about the magnetic dipole moment of a revolving electron. Suppose an electron undergoes circular motion around the nucleus as shown in this figure. The circulating electron in a loop is like current in a circular loop, because an electric current is nothing but the flow of charges. The magnetic dipole moment due to current carrying circular loop is given by this expression mu L equal to Ia, and in magnitude mu L equal to Ia. Here there are vectors. If the time period of revolution of the electron is given by t, then the current due to circular motion of the electron is given by I equal to minus E by t, where this minus E is the charge of an electron. If r is the radius of the circular orbit and v is the velocity of the electron in circular orbit, then we have t equal to 2 pi r by v. And equation 3.46 and equation 3.47, we get mu L equal to minus EVR by 2, where this A equal to pi r square, that's the area of the circular loop. By definition, the angular momentum of the electron about O is given by L equal to R cross P, and in magnitude L equal to RP, that's equal to mv into R. Just P is the momentum. That is given by the product of mass and velocity. Using the equation 3.48 and 3.49, we get this expression. It's mu L by L equal to minus E by M, E by 2M into L vector. This negative sign indicates that the magnetic moment and angular momentum are in opposite directions. And in magnitude, mu L by L equal to E by 2em. Substituting the values of this E and M, we get this value for mu L by L. This mu L by L is a constant, and that is called as gyromagnetic ratio E by 2m. It must be noted that the gyromagnetic ratio is a constant of proportionality, and that connects the angular momentum of the electron and the magnetic moment of the electron. And according to Newton's quantization rule, the angular momentum of an electron moving in a stationary orbit is quantized, which means L equal to nh, that's nh by 2 pi. The h is Planck's constant. This is nh cross. This one L is the angular momentum is given by nh cross, where h cross is equal to h by 2 pi. Here h is the Planck's constant, which has a value of 6.63 10 power minus 34 joules second, and the n number n is an orbit number, which is given by 1, 2, 3, etc. So mu L equal to E by 2m into L. That's given by NH by 4 pi m. And substituting all the values of EH, m in this equation, we have mu L equal to n times 9.27 10 power minus 24 ampere meter square. The minimum value of magnetic moment can be obtained by substituting n equal to 1. So we have mu L equal to 9.27 10 power minus 24 ampere meter square. It can be written in terms of this joule per t. So mu L minimum is given by mu B, and this mu B is given by EH by 4 pi m, and that's given by 9.27 10 power minus 24 ampere meter square, and that is called as Bohr magneton, and that is used to measure atomic magnetic moments.